No more, any other homework questions or anything? Okay. Anybody still need to borrow a calculator? We're going to finish this up. We're going to do some other stuff. You're going to need a calculator for it. Anybody need a z-score chart too? Come on up here if you need something. Make sure it's got battery. Z-score chart. It's been kind of written on. Make sure it's got battery. Okay. All right, guys. Oh, I got somebody's glasses. Hello. So coming back to this, if there's no other questions from homework or anything. So last time we did this. We did this side. So let's do this. Let's kind of review what we know so far. We know this up here, right? Yeah. Make sure it's got battery. Oh yeah, thank you. This guy, right? So you guys got to sit through yet another one of my conceptual explanations. It's the best thing in the world. It's not torture at all. We developed this formula here. What's nice about this is normally you are going to know everything except Z. Right? You're going to know everything except Z. Can anybody remember where does the Z come from in one of these kind of problems? Spiders? Okay, we did talk about spiders. The spiders will deliver it to you. Right? You must follow the spiders to the forest. Anybody remember where the Z comes from? How confident you want to be. And it makes sense because the Z kind of basically tells me how far away from the mean I want to get. So if I want to be more confident, I want to cast a wider net. I want to go further away, so my Z-score is going to get bigger. So there's a direct connection between how confident you want to be and the Z-score you're going to use. Okay, I like it. So we did those problems. This time we talked about dolphins, just to take a little breather from spiders. And then, once we finish this, before we finish it, we did create one more formula. And can anyone remember what that formula's purpose was? What is my purpose? Pass the butter. Huh?
Find the number.
Find a number needed to make what happen? The error to be some certain amount, right? You guys semi with me. So just to remind you on this paper, for the dolphins, when n was 37, we got an error of 1.324 inches, right? Down here we determined if I want an error of half a frickin' inch, which is quite a step down, I need to push my sample size up to 260. And again, why does that make sense? A bigger sample's better. We knew that from day one. What does better mean in that case? Better means I'm more certain about what I see. If I take a bigger sample, I am more certain about everything. You guys with me? If I sample 2 people from Grossmont randomly, how certain am I that their average age is equal to the actual average age? Not very. Would you agree with me? If I take 300 randomly selected, I'm a lot more certain about the sample mean, the sample standard deviation. I'm more certain about everything. So it makes sense that the error part, if I boost the sample size up, the error is going to go down. So this enables, if I have a target for my error, I can predict how big of a sample I should take. And I think I said last time, it's sort of like a feasibility study. If this comes out to be 100,000, no. Not for us. We don't have the resources to go talk to 100,000 people. But if this comes out to be 120, yeah, okay, we can do that. That's feasible. Okay, how we all doing? That's a recap of what we did, right? Okay. So, then we developed another formula. This one is for means when I know the population standard deviation. That's what that's for. This one is for what? What is that one for? Say again? Yeah, these are all for like samples, but so that one is for getting an estimate for a sample mean, for a population mean from a sample mean. What's the little hat dude? What's P mean? What's P mean? Okay, probability. I would accept that. A percentage, right? If I see it without a hat, that's a population percentage. So if I see it with a hat, that's a sample percentage. I like it. So we'll do some examples of that. I think we stopped short of actually doing an example. I think the last thing I did was we developed that formula, and then we left pretty soon after that. Okay. All right. Okay. So that basically catches us up to where we left off. One big thing that we still need to talk about is related to this. This problem here. How did I know I could use z-scores to do this problem? What was it about this problem that said we could use z-scores to do this problem?
It's normal distribution.
Yeah, why was it normal? Oh, it does say that, but I wish I wouldn't have said that. Why did I not need to say that? You're right. Either it's going to say it's normal. If I didn't say it's normal, why would we still be able to do it? Yeah, n is 37, which is bigger than 30. Kick-ass. That is for means. That is how means work. That's the test to know if I could do normal stuff with means. Are you guys with me? We need to develop, what if I have freaking percentages? Is there a test to tell when they are normally distributed? And n greater than 30 is not good enough, and I'll show you why. Let me bring back, there's an old handout we did a while back, which I forgot to print out, so I just have it up here. You guys remember that guy? You know, like, I can't even remember what you just said 2 minutes ago, John. No. You guys remember that handout? No, it's okay if you don't. It's okay. So this was a histogram showing all the probabilities for flipping a coin 14 times. So it's basically, if you use the binomial formula, blah, 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 for each one of these number of successes, I can then plot them, make a histogram, whoop-de-doo. So at the time, I mentioned, does that look normal? Does that look at least roughly normal? Does it look actually pretty good in normal? And that looks really good. I mean, it's perfectly symmetric. It goes up and it comes back down. It looks really freaking normal. Yes? Would you guys agree? Good, right? And you didn't have to, but it's good you did because it's true. All right. So what is it about this? What was the mean for this? If I flip a coin 14 times, what's the expected number of heads? 7. 7 is right in the middle of the picture, correct? So watch this. What if multimedia experience. Why was the mean 7 exactly? What's the formula for the mean for a binomial? It's the greatest little formula for the mean ever, as far as we know. Huh? N times P, kick-ass. So in this case, it was a fair coin, 50%, 50%, so 50% of 14 is 7. Kick-ass. Do you all agree with me that the lowest number of heads I could get is 0? Good. All right. And the highest number in this case would be 14 because they only flipped it 14 times. If you flip it 14 and you get 15 heads, something is happening to you. Okay. Now watch this. What if I had a coin that was not fair? It was weighted. And it was weighted in such a way that it only came up heads 1% of the time. Is everybody with me? This one's based on a fair coin. So if I flip a fair coin 14 times, I expect it to show up as 7 heads, correct? Now, it could see 6 or 5 or 4, but to get 12 would be really silly, unlikely. You guys kind of with me? So I could figure out, for example, we actually did the min and max usual and determine when would it be evidence that somebody's tampered with us and so forth. You with me? So what if I had a coin that actually only came up heads 1 out of 100 times? What would the mean be if I flipped it 14 times? What would the expected number of heads be if I flip it 14 times? Well, what's the formula again? N times P. And what is 14 times 0.01? 14 times 1 is 14. 14 times 0.1 is 1.4. 14 times 0.01 is 0.14. Is everybody with me so far? So this would be a very weighted coin. Right, somebody sneaks that into the Super Bowl and they do the whole thing. Pull it in there. Okay. So very different from what that would look like. Why is the tallest peak where it is on that picture? Why is the tallest peak right at 7? What was the expected number of things for the heads for this one? 7. So doesn't it make sense that the tallest peak should at least be close to the mean? Because that's the expected number I expect. That should be one of the most likely things. Are you guys with me? Where would the tallest peak be for this picture? What was this guy's mean? What was this guy's mean? 0.14. Like somebody's like, it's right there, Jeff. I know. I just want you to say it. So the peak for this one would be at 0.14. Which means every other thing is going to be shorter and it's going to get less and less and less likely as they go away. Does that look normal? Does that look normal? Shit, no. Why exactly does that not look normal? I'll accept a few things. Because the peak should be in the middle. It should be symmetric, blah, 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 right? You guys with me? So I really want you to understand. If I made P.01, the tallest peak would be here. And then every other peak would go down. That is totally not normal, right? If I pull it away from that wall far enough, in this case it's at 7, now it's got room to go up. Also, it's got room to come back down, right? I really want you guys to be with me. So if this tall peak was there, what would make that happen? The mean would have to be small. That would put the tall peak here. It wouldn't have enough room to go up and then come back down, correct? Also true on this side. If the mean was too big, it wouldn't have room to go up and then come back down, right? Okay, maybe. So I want it to be in the middle. So let's see if this makes sense. If the mean was at least 5, it would have room to come up, right? It would have room to go up. In this case, it would also have room to go back down, correct? Now, I'm going to have 2 requirements. That's just one. Why do I need 2 requirements? Because I have 2 walls. I can't let it slam against this dude, because then it's going to start tall and go short. That's no good. And I can't let it slam against this dude, because then it's going to end tall, so it's only going up. So let me do this more specifically. NP has to be greater than or equal to 5. Here's what's kind of interesting. NQ must be also greater than or equal to 5. Let me make sure you guys are with me. NP, in this case, is 0.14, right? You with me? That means I expect to get 0.14 heads if I flip it 14 times, many, many times. Are you guys with me? Can anyone tell me how many tails I would expect? to get? If I flip it 14 times and I expect to get 0.14 heads, how many tails do I expect to get? I flip it 14 total times. I expect to get 0.14 heads. How many tails do I expect to get? 13. Okay, 13.86. The rest, right? You guys have calculators, and some of you guys borrowed them. You can use a calculator. It's got a total of 14, correct? If I flip a coin and expect one head, how many tails do I expect? If I flip a coin 14 times and I get one head, and I expect one head, how many tails do I expect? 13. Good. So I'm just doing the same damn thing with a grosser number, right? Are you guys with me? That would be NQ, what I just said, right? So both NP, that is pulling it away from this wall, and NQ, that is pulling it away from that wall. If they're both bigger than or equal to 5, it's in the middle, it's got room to go up, and it's got room to come down. And then it can look normal. It can be normal. So this dude is perfect. What was NP here? It was 7. What's NQ? 7. They're both bigger than or equal to 5. That's why that sucker looks so freaking normal. Okay. Maybe. So for means, what's the test? For means, if it doesn't say it's normal, what do I check? For means, what do I check? We all know this. N's got to be greater than 30. Beautiful. Percentages does not work that way because, for example, what if I flip a coin 40 times? Right? That's bigger than 30, correct? But what if the probability I get ahead is 0.001? What would the mean be then? Once, twice, once, twice. So it'll be 0.04, I believe. Is that right, Jeff? I don't know, Jeff. Thank you, okay. That's stupid small. So where would the highest peak be? Here, right? I really want you to see how for percentages, n greater than 30 is not good enough because p could be so damn small, it's got no chance to go up and come back down. You guys see that? So I wanted to make sense why the test is different. For means, it's just n greater than 30. Yay. For percentages, damn it, I've got to check NP and NQ. Basically, so it's in the middle, so it's got room to come up and room to go down. That's exactly why that looks so normal, because it's got room to go up and room to come down. Okay, maybe. Okay. So, with that knowledge, let's look at this. I think this is from, it doesn't matter. Okay. And I don't know if anybody just got in here. If anybody still needs this handout, let me know. So the other side was dolphins stuff. Everybody got this handout? Okay. So somebody remind me, what's P hat mean? The little hat on him? What's P hat mean? Sample percentage. Just like X with a little bar on his head is the sample mean, P with a little hat on its head means the sample percentage. And I did say that. Do you guys remember the symbol's name? It is P hat. Right? So that's the thing. You don't want to wear that. So P hat. Thankfully, that's all the clothing the P's and Q's are going to wear. We don't have P shorts and Q socks and such. Okay. So take a minute. If I just said, yeah, we talked to 652 voters and 459 of them voted in the last election, could you figure out the percentage that voted? That would be P hat. Well, how would you figure out the percentage that voted? How many total people did I talk to? 652. Out of 652, how many voted? 459. So 459 out of 652. The exact way we say it in English is the way we do it in Mathish. So somebody help me out. What is 459 divided by 652? I'm going to crowdsource it. And I'll tell you this, I need it rounded to at least 3 decimal places. 704? Okay, I like it. So what's Q hat then? I don't care what clothing they're wearing, P and Q have to add to be 1, right? So what's Q hat got to be? 296. So you just got to do 1 minus that, right? Is that right? And by the way, right here, X means exactly what it used to mean. It's the number of successes. And of course, N means the same thing always, which is great. The total number of things. So N, of course, we already know is 652. So now you know what I mean when I say this. And by the way, I should have said this before. If I don't know mu, what's the next best thing I could use? If I don't know mu, what's mu? Of what? Population, right? So if I don't know the mean of the population, what's the next best thing I could use? Sample mean. I love it. So if I don't know the population percentage, the next best thing I have to use is sample percentages. So take a minute and just figure out what NP hat and NQ hat are, and then I'll show you a bit of a shortcut. Who's got this figured out? $459.008. Do you notice how it's? And if you think about it, real quick, you guys see that? Isn't this basically that? And of course it is, because freaking P hat is X divided by N. So what's N times P hat? Freaking X, right? So there's a bit of a shortcut there. And if you don't understand it, you never have to use it, but it's there. And Q hat is just the rest. So if I just do 652 minus 459, I get 190 something. 193? 90. So it'd be 192.992. Yes? Okay. Which is 193. Yeah. But if you do 652 times 0.296, you will get what you just said, which I already forgot. 192.996? 992. There you go, Jeff. Good job, buddy. What's the most important thing up here, though, is both of those numbers are what? Crazy. You know, both of those numbers are? They're greater than or equal to 5, yes. What the shit does that mean? What does it mean? They're greater or equal to 5. Whoop-de-doo. What does that mean? What does that mean? Yes! I like it. So, the whole discussion we just had. That's just like saying N is 47, which is greater than 30. Therefore, it's normal enough. NP and NQ hat are both at least 5. Therefore, it is normal enough. I am allowed to do this problem. So officially, if you did NP hat and you got 4.3, you can't do that problem. It's not normal enough. Poor little problem. Is everybody with that? So that's new, but I really, really hope it makes sense. To me, it's actually nicer than N greater than 30 because it's got a visual idea to it. It's got to be pulled away from the wall so it's got room to go up and come down. N greater than 30, I had to do alternate units Florida for that thing, which was weird. Now, don't say anything. Take a minute. Can you figure out, you know I was going to do this. Is that one on the baby chart? Remember the baby chart? Let me remind you about the baby chart. So if I would have said 95% confidence, I know the z-score is 196. So Jackass Jeff said, nuh-uh, 96% confidence. So take a minute, see if you can figure out what the z-score would be for a 96% confidence. Don't say anything. And also don't look up 0.96. That's not going to tell you anything.
We have to draw.
You don't have to, but I would highly recommend it. Oh, that's not useful. Yo.
Deciding factor to make it normal? Making it normal?
The fact that both NP hat and NQ hat are bigger than equal to 5. Visually, that takes the peak and puts it more towards the middle, so it's got room to go up, come down. That makes it come out to be normal enough, right? If that peak is too close, if it's less than 5, it's too close to one wall, doesn't have room to go up and then come back down. Does that make sense?
Yeah.
If it's too close to one wall, it's already up. Shit. So I got to take it away from that wall and away from that wall. That's why there's 2 requirements to meet to get it in the middle.
So it'll always be 5, right?
Always. Always. Yes. Okay. All right. What are we doing? I forgot. Oh yeah, z-score. Did you guys get the z-score? What is it? 1.75? Does that sound all right? So for 95% confidence, what was it? If I wanted a 95% confidence, what was it? 95% confidence is 1.96. Yes? Now I know what you guys are doing. So I would expect 96% confidence. I'd have to go out a little bit more, wouldn't I? So I know the z-score is going to be bigger than 1.96. So 1.75 doesn't make sense. So let me show you what you did. 96% inside, correct? What's outside? 4% total, 2% on that side. If I look up 0.02. Chibo. Again, this chart only understands areas that are below a z-score. 96%. That's in the middle of 2 z-scores. This chart doesn't have a freaking clue about that shit, right? So if I draw this, here's 96%. Oops. I need either one of these 2 z-scores because they're both the same number, just negative positive, correct? Because of the symmetry. So I always go for this one. 96 inside, 4 outside, 0.2. So now I have an area that is below one of the z-scores I want. This can help now. It can only understand areas that are below a z-score. Do you guys understand? So did some of you guys look up 0.96? I think that's what happened, yes? Okay. So don't do that. So if I look up 0.02, or you could look up what's below this z-score, what's below the positive z-score, what total area is below it? Not just 96, so how much? 0.98. So if I look up 0.98, where'd it go? Where are you? There it is. I get the same number, just positive, 2.05. Yes? And it makes sense because 95 is 1.96. 96, I just have to push it out just a little more to catch 1 more percent. So it makes sense the z-score is going to be a little bigger than 1.96. Okay, so in my z-score, 2.05. Don't ever make the z-score negative. Like the first z-score I found was a negative z-score, but I just need the number because the plus or minus is already built in, correct? I'm already going up and down. I just need to know how much. What's the number I go up and down? Okay. So now it's just plug and chug. So I'll wait. Go ahead. Plug all your stuff in there. It's going to be plug and chug, and then can you put it in the calculator correctly? So let's see what happens. Well, we know all this stuff. I don't know why Y2 got all dramatic, but there it is. Just plug in P hat, Z, P hat, Q hat over N. So now it's a question of getting this sucker in the calculator correctly. So what I would do is I would do the error first, just like before. 2.05 times square root of, and I've got my calculator set to old style. So currently my square root symbol does not grow, so I'll do it both ways. Square root of 0.704. I just don't want to close these parentheses until I'm done putting all my square root stuff in. 0.704 times 0.296 divided by 652. So I got that. And just to show you, if you have a newer calculator, what it would look like. It would look like that. The square root symbol just grows, which is nicer. It's much more visual to make sure you got all the stuff in there that you need. Is anyone not able to get that number? Is everybody all right? Okay. Technology day is always exciting because there could be all kinds of errors. But nobody's speaking up. Okay, I'm going to assume everybody's good. So now that's my error. That's how much I think I'm off by. So in general, what you really should do, what you really should do is go one more place out here than what's there, and then round at the end. But, you know, I'm not going to be horribly, like, draconian about that, but you don't want to round too much too early. So a general rule of thumb is, and I know rule of thumb is not the greatest expression, but a general thing to go by is your error should be one more decimal place than this. But if you don't do that, it's not the end of the world. And I don't know if you guys remember I did this weird little dude. Store that in X, and then I can go 0.704 minus X and 0.704 plus X. And you don't have to do that either if you don't want to. So they're pretty good. Okay. So what the hell does those numbers mean? I got some numbers. What do they mean? I got two numbers. I got them. What do they mean? Sure. So that defines my confidence interval, the lower and the upper. So you always put smaller number first. Get over here. 667 up to 0.741. So round, please. The end result needs to have the same number of places as this did. But if you go more, it's fine. Okay. Now what about this? What do I want here, this dude? Who remembers how that starts? We are 96% confident that the interval. Now watch this. You always need units. The units here will be percentage. So convert these to percentages. We are 96% confident that the interval 66.7% to 74.1% contains what? Yeah, and then you can plagiarize a little bit. The true proportion of people that voted. Proportion? Good job, Jeff. Proportion of people that voted. So basically every confidence interval statement is going to go, we are such and so confident that this interval contains the true something. It's always going to have that cadence to it, that template. Okay. All right. Very quickly, a little bit of algebra to add to your day. Let's see. You can keep that, Jeff. No, I got to share it. Do you remember we did a little bit of algebra with the other? So in this formula here, you always agree with me that this is the error. That plus or minus piece is the error. So if I say error equals this business, and then I want to solve for n, because I want to be able to do the same thing we did before. How big of a sample do I need to get the error to be such and so small, right? Are you guys excited about solving this for... I don't blame. So the first thing I could do is like square both sides. Is that all right? Now let's see if anybody remembers. There's a really cool thing that happens in algebra when you have a number equals some fraction. You can just shibboop. Do you guys remember we talked about that? I don't know if you guys, you're like, you can make sound effects, Jeff? Yes. 10 divided by 5 is 2. 10 divided by 2 is... These just switch places and it's still a true statement. Of course it is. 10 divided by one chunk is the other chunk. I don't care which chunk you divide by. Sounds like how much wood could a woodchuck? So the n and the e squared can just switch. And there's the formula. Sorry. Some of you guys have these poker faces, but some of you guys make up for that. I love it. This poor little hat. All right. So I've got it right here. There it is. One general thing that happens I've noticed is students will sometimes see how this is number 1 and see how this is number 2. See how they have nothing to do with each other. This is a totally different problem, right? So none of this should show up here. So look at this. How many people would we need to survey to be within 3% of the true proportion of students who passed statistics the first time around at 99% confidence? Can anyone see what E is? Yes! Kick ass. 0.03. Percentages are made up bullshit. If I want to do math to something, it better be an actual number. So make it into a decimal. Now, can you figure out the z-score real quick? This one's nice. How confident do I want to be? Much more confident than normal. So now I can use the baby chart, right? Baby chart. I did it. I just did it. I'm sorry. What's the z-score going to use? 2.575, right? I want the confidence level to be 99%. 2.575, kick ass. Now, what's P hat and Q hat? Do I tell you? I don't tell you shit. So, can somebody tell me, let me think, what's a good example? If I flip a coin 1,000 times, can somebody guess the percentage of heads I flipped? 50%. So in general, if there's something I really have zero idea about, my best guess as the percentage of that is 50-50, right? Stay with me now. Does everybody agree on this problem? I don't know what p hat and q hat are, right? So one way to look at why we do this is my best guess for the p and q is always 50-50 if I have no idea. Does that make sense? Okay, moving on. Mathematically, if there's something we don't know, should we be rewarded or penalized for that? This is not about you, but this is general. So mathematically, if there's something we don't know in an equation, should we be rewarded for that or penalized for that? Penalized, right? There's something we don't know. We don't know what p hat and q hat are. If I make p hat and q hat both 0.5, that makes n the biggest it could possibly be. So I really want this to make sense. How big of a sample should we have to take if there's something we're not sure about? Well, we should have to take a bigger freaking sample than normal because we're not sure about something, right? Does that make sense? We've got to cover our ass a little more for not knowing something. So, in general, if you have this kind of a situation where you want to use this equation and they don't tell you what p hat and q hat are, you guess 0.5. So now I can set this up. I know z. I'm guessing p hat and q hat. And I know what they want the e to be. So now I just throw all that in the old calculator. $1,800. Trying to do in my head. It's gonna hurt. All right. Okay. Anybody got that? Anybody got it? Okay. 1841 point stuff, right?
Yep.
Well, it doesn't matter what the point stuff is. You always, if it's a decimal, you round up. So now look at part B. What's different about part B? It's the same question, except what have they done? What have they done? Same question. I want to be within 3%. I still want to be 99% confident. This is still the same problem, except now we've done a preliminary study. Can you see a p hat from that preliminary study? Is there a p hat you could create? Is there a percentage? What is it? How do you calculate it? 31 divided by 42. Reading somebody's lips out there. Out of 7, so 0.73. I don't know. What is it?
738.
738. Okay. And then Q hat would be what? That's right, kids, 0.262. And then you just throw that stuff. Now it's the same exact formula, except we didn't have to assume 50-50. We now know it's this. So let's see what happens to the required sample size. Oops. Yeah. So that's going to be 3/4, 3/16 versus 1/4. 3/16 versus 1/4. You can do it, Jeff. So it's going to be 3/4 of that, which is, I don't know, 1,300 something. For somebody save me from myself, please. No, not yet? Okay. What is it, sorry? 1,425? Okay. I got close. And that's after rounding it up?
Yeah, it was.
Okay. So 1424 point stuff? Okay. So we need over 400 less. Still 1,400 people, but I need over 400 less, which I'll take, right? So this is why, have you guys, I'm sure you guys have heard this, the phrase preliminary study at some point in your life, your time roaming this earth. That's why what's one reason why we do a preliminary study is it improves our prediction about how big of a sample we should end up getting. So let me answer the actual question. How many more students would we need? Well, how many students did we already talk to? 42. So how many more students would we need? 1,383. Yeah. Now again, if I ask this question on a test and your answer was 1,425, I'm not going to take points off. That's the right answer. But if I say how many more, you should subtract whatever we already did. Can't like it, maybe. Yes?
Where do you subtract it, though?
Oh, we already talked to 42 students, right? We just found out we need 1,425 total. So if I subtract 40, I can see how many more I've got to talk to. Yeah. Okay. Very exciting. So I appreciate everybody remaining calm. All right. Not too bad, right? I mean, I don't want to make any assumptions, but confidence intervals are really an example where the concept is it's nowhere near as much as what we did with central limit theorem, but still, it's a little bit out there. I talk about spiders and islands and dolphins and whatever. But then the nuts and bolts of it, it's a lot of just plug and chug. Normally, we only have to determine one thing, the z-score, and that's based on the confidence level, right? Everything else is just kind of given to us. Okay, all right. I'll stop trying to sell this. You're going to have to do it either way, even if you don't like it. Okay. So, what are we going to talk about today? Well, because this is just review based. Now we're going to start talking about what happens if I don't know this. If I don't know the population standard deviation. Okay, and you're all like, I wasn't really worried about that. Okay. Does anyone here, again, this is not a prerequisite. Anybody here drink Guinness ever? Anybody know what Guinness is? Okay. I personally don't like it. Drank it in grad school because my physics teacher liked to drink Guinness, and I would go to the bar with him afterwards so I could just ply him for what was going to be on the next test as he got drunker and drunker. And I just kind of sip my nose. Okay. But the idea we're about to get into comes from somebody who worked at the Guinness Brewery way back in the 1800s. So this guy worked at the Guinness Brewery, and he was trying to do some research to see certain things, and he had to develop this new approach, but he didn't want to report it out with his name because he had a contract where anything he did at the company belonged to the company. So he actually published this stuff under a pseudonym. He just called himself Student. So his name was William Gossett. You don't have to memorize that. I'm not going to quiz you about this dude. But what he was working on was exactly what I just said. What if I don't know the population standard deviation? So what did we just say a minute ago? If I didn't know p hat and q hat, I had to kind of penalize myself. I had to make the math work to the point where it made me have to take a bigger sample. Are you with me? So if I'm constructing a confidence interval and there is something involved in there that I'm not sure about, should I have to make my interval bigger or smaller to cover me for that? Bigger, makes sense. So what I like to say is if there's something you don't know about the formula you want to use to make a confidence interval, you got to make it bigger to cover your ass for not knowing that thing. So if I don't know sigma, what's the next best thing I can use? Yes. What does sigma mean again? What's x bar? What's x bar? So we took a sample, correct? If I don't know the population standard deviation, I must instead use the sample standard deviation because I just took a sample. Of course I can calculate a sample standard deviation. Are you with me? Do you agree with me? Do you agree with me? Sure, Jeff. Do you agree with me that if I take a sample, I can always find the sample standard deviation if it's quantitative data? Are you guys with? You take some data, you can always find the sample standard deviation, right? I'm only ever going to use it if I don't already know the population standard deviation. Does that make sense? I might be making a fine point of this because the book might have homework problems that do exactly this. They're going to give you both, and you're going to go, nice S, I'm going to use freaking sigma. Of course I am, because that's the more definitive thing. Are you guys kind of with me? A little bit? No? Okay. So here's the problem. If I use S instead of sigma, do you think that S will equal sigma in general? In fact, I would put money on it not being equal to sigma. Are you with me? Just like a sample mean. I would put money on it not equaling the real mean of the population, right? Okay. So when I throw that into the formula, leave this blank. By the way, real quick, students get a little confused about this. Do you see how I still divided by the square root of n? Of course I did. Dividing by the square root of n does not make that become a sample standard. No. What does this make it become? What is this? What was that? That's good for what? What is that one good for? And you're all like, what is that? Individuals, right? Remember? That one, it comes from individuals, correct? We did it back in section 2.7. We had individual data values. We made a table. We figured out how spread out those individual data values were, correct? What does this do? Makes it into a standard deviation of?
What's that?
Groups, right? So if I divide by square root of 11, I've now made it into how spread out groups of 11 would be. It doesn't make it become population to sample. No. What's S? S is a sample standard deviation for individual data values. So if I take a sample, I better frickin' turn it into a standard deviation for groups. So I have to do the same thing for both. Okay. So some students get hung up on, why do you do that? It's already a sample standard deviation. No, this is individual spread. I need how spread out groups are. I still need that. Okay. So here's the thing. We all agree, I believe, that S is just an approximation for sigma. Anytime I have something I'm trying to throw into my equation that I don't know something about, I want to make my interval bigger than it would have been otherwise, just to cover my ass for the fact that there's something I don't know. Let me let that sink in for a minute. Okay. All right. Does that make any sense? If I've got a formula I'm trying to use, I'm trying to put something into it that is a value that's an approximation for what it really wants, there should be some kind of a penalty for that. There should be some kind of a adjustment for that. So in this case, it makes sense that I'm just going to make my confidence interval a little bigger than it would have been. That'll cover for me not knowing what the real standard deviation is. So what we use then, what William Gossett came up with when he was working at the brewery, I love that word, he came up with a slightly adjusted distribution. Jeff, you already have blue. Oh. So it's just going to have the letter T instead. So we have z-scores and we have t-scores. Now what really kicks ass is you're going to have both of these formulas on a formula sheet, correct? So then, when do I use z-scores? When I know the population standard deviation. When do I use t-scores? When I know the sample, when I only know the sample standard deviation. It's right there in the formula. I don't let you use notes, but the formulas are notes. Okay, maybe. So, guess what's going to happen now? Not yet. T-score chart. I don't know if anybody's sitting there going, when do they stop these charts? We have one more chart after this. And that'll be it. Which is maybe 3 too many from your perspective. Uh-oh. See you. All right, guys. Anybody have any observations about this chart you want to make? Do you see anything on here that's familiar, not familiar, whatever? I mean, if I were you, the first thing I would notice is this shit, right? So we'll talk about that in a minute. Do you notice if you go all the way to the bottom, what's it say? Large. You gotta like that. That's most interesting. Large. Oh, sorry. So watch this. Guys, look at me real quick. 99% confidence. What was the z-score for that? We just did a problem like that. 2.575, right? What about 95% confidence? We did that also, right? So 99%. Z was 2.575. 95% was 1.96. I love it. Now watch this. A t-score's job is to widen the confidence interval when I'm using something I'm not sure about. So in this case, I got S instead of sigma. I don't know if S is really close to sigma. So the t-score's job is to widen the interval. If I take a sample, how could I make myself more confident in what the sample statistics tell me? What kind of sample should I pick? It's always random, so don't say that. We're always assuming it's a simple random sample. How do I make what I see, how do I make it me trust what I see more? We talked about this earlier. So bigger sample, right? If I take a bigger sample, I will trust what the sample gives me more. Does that make sense? You know this from day one. If my sample size gets big, my t-score does not have to make my interval as wide. The bigger my sample gets, the less I need a t-score to help me. If my sample gets large, I can then use z-scores. Are you guys semi with me? Now, why does it say large and not a specific number? Because it's frickin' subjective. Anything past 2,000, it really depends. Do you have to be very, very precise? Well, then you better frickin' get technology to tell you exactly what t-score. Do you not care that much? Then shit, you could use a z-score, whatever, right? So, one thing I want to point out, what is this column all about? Degrees of freedom. Have I said that before? Degrees of freedom. We talked about that. So remember that was the n-1 thing. That was me explaining why the standard deviation back in chapter 2 is divided by n-1 for a sample. I don't know if you guys remember that. So if I have a sample size of 7, where am I going to look here? 6, because the degrees of freedom is n-1. So look here. Now what about tails? Well, you guys tell me. If I make a confidence interval, don't I chop it like this? Chop. And I got 99 or whatever percent. You with me? What percentage is in the tails if there's 99% in here? What total amounts in both tails? 1%. With me? 2 tails, 1%. Now this is a little more precise. Remember it was 2575? This is a little more precise, 2576. Why was this 2575? Because on the z-score chart, remember when it was right in between 2? Are you kind of with me? So here it's just a little more precise. It's basically still 2575, right? What about 95%? What's the area in the 2 tails if I have 95%? 5%. So if we go 5%, 2 tails, go all the way down, there's the z-score, right? Crazy shit. So this, I no longer need this. In fact, this has outlasted its usefulness because this captures all of these plus some more. Do you guys see that? So if I'm using this chart, if I stop, I get a t-score. If they go all the way to the bottom, I get a z-score. So we will be using the t-score chart to sometimes get z-scores because they live at the bottom. Now watch this. 1.96 is the z-score. The minute my sample starts getting smaller, I'm less and less certain about the S I get. The standard deviation of the sample could be further and further away from the real standard deviation. So I got to cover my ass more and more and more. And as my sample gets stupid small, I got to cover my ass quite a bit. You guys with me? That's why it makes sense that as they go down, the t-scores are getting smaller. They're approaching the z-score. I don't need them as much anymore. I'm like, thank you, but I'm getting a little more certain about my stuff. I don't need you to push that out as much. How you guys feeling? I want you to understand. I appreciate that response. We are in, again, the conceptual stage of things. The end nuts and bolts of this are this formula. You looked at your z-score chart to put a number there. Everything's going to be the same, except now we're going to look at the t-score chart to put a number there. That's the nuts and bolts of it. You just have to know when to use which, right? Okay. So let's do this. I've got the handout. You know me. So I want you to do the first 3 problems on this. One of them's going to be a little freaky. So just the number 1 on this. That's all I want you to do for right now. So number 1 is basically just, can you read the chart correctly, right? And just like before, guys, hopefully it's not too late. Don't write on this. You can put your name if you want to. You're going to use this on tests and such. Don't put notes on here. Okay. So if you're just staring at me, that's not good. You should be working on this, the first 3 problems. Yeah, I'm sorry, man. I thought I gave you a copy. Okay. Interesting. All right. So, guys, these first two need to be very straightforward. So, degrees of freedom is, I won't say always. As far as we know right now, the degrees of freedom is n minus 1. So, what's the degrees of freedom for part A? 5. So, now I know I want to go to 5. Now, real quick. In chapter 9, we're going to see a very specific reason why they've broken it out into 1 and 2 tails. I always just use 2 tails for confidence intervals, but for example, 99% confidence, how much is in both tails? 1%. If I do cut it down to 1 tail, that's 0.5%. Both of those are still the same column, right? So you can't go wrong. So I'm going to stop at 5, and I get, looks like 4.032. How are we doing? Makes sense. I want to be really confident, but I have a very small sample size. So hell yeah, I'm going to have to push that interval way the hell out. Okay. Okay. What about part B? What's the degrees of freedom? 100. That's on the chart, which is nice, Jeff. 100's there. What column do I want to look at? I want to be 90% confident, so I want area and 2 tails is 10%. So then I want to go, got it. Down to 100, and I get, looks like 1.660. Okay. Now, anybody try C yet? What's the degrees of freedom? 92. What sucks about that? Not on the chart. So in general, again, this is the trade-off. Because you have a teacher who is opposed to just pushing buttons, we're not going to get as much resolution on things. Do you notice, real quick, do you notice how it's going by 1s and then suddenly it starts going by 5s and then 10s and then 100s? Because they're not changing as much, correct? So anytime you have a value that is not on the chart, you go to the next one below it, above it on the chart, but below it. So what's right below 92? 90. So I'm going to go to the degrees of freedom of 90. Which column am I looking at? I want 98% confidence. So which column am I looking at? Yeah, the second column. So therefore I want 2.368. Is that cool? Okay. Yes. All right. Now, in order to be able to use a z-score, what must be true about the distribution? It's got to be normal. We have 2 ways to check if it's normal. In order to be able to use a t-score, the same thing must be true. T-scores are just sort of like z-scores pushed a little bit. So I still need to have a normal distribution. You guys understand? So if it's not normal and the sample size is not big enough, I still can't do shit. 2A. Sample size, is it big enough? But what saves me? What saves me? Yeah, they tell me it's normal, correct? Okay, so it's got to be one of those two things. They either have to tell me it's normal or the sample size has to be big enough. All right, so it's normal, correct? So it's got to be normal to be able to do any damn thing. What tells me which score to use, Z or T? Why were T-scores invented? To cover our ass for when we don't know what? The population standard deviation, if I only know S. So in this case, which one do I know? Of the population. So be really careful. I always get somebody tell me, we know the standard deviation, so we can use Z. No. Which standard deviation, right? T-scores were invented for situations where I don't know the population standard deviation. I only have the sample standard deviation. That's why they were invented. So on part A, 2A, I'm allowed to use Z-scores because it's normal, check, and sigma's known, check. So go ahead and figure out the Z-score I would use. And if I were you, I would use the T-chart. You're like, you ain't me, Jeff. Yeah. But if I want to be 90% confident, which column would I look at? 1, 2, 3, 4, 5. Which column? The fourth one, right? 90% confident has 10% out and 2 tails. If I stop, I get a T-score. If I go all the way down, I get a Z-score, so I get 1, 6, 4, 5. So T-score chart kicks a lot of ass for finding both Z and T. So this will be 1.645. All right, you guys keep going. Do B, C, and D. So for this one that says it's not normal, so is this the one I can't do? Why can I do this one? Yeah, it's the sample size. It says it's not normal, but it doesn't matter because n is greater than 30. So that tells me I can do something. Is it Z or T I can use? I have to use T because I only know S. That's a sentence that would have made no sense before today. And now I have to look at the T-score. What's the degrees of freedom? 38. And then let me introduce the symbol. I always forget the symbol. Let me do it right now before I forget. Let me draw this picture just to make this make more sense. So 98% confidence. So what area is in the tails? 2%, right? So the total area in the tails is 0.02. The symbol we use for the area in the tails is really a perfect symbol. We use the Greek letter A for area, and it happens to look like a freaking fish, okay, that has a freaking tail. That's too much to believe. So the area in the tails, we use a symbol that's a letter A, and it has a freaking tail. You can't beat that shit. So whenever you see the letter alpha, that means the area in the tail or tails. Confidence intervals always make 2 tails. Chapter 9, we're going to see some stuff that makes just 1 tail. But right now, we're dealing with 2 tails all the time. Okay. So 0.02, and that's what these numbers are really, right? That's alpha. So 0.02, stop at 38, and you get what now? 2.429? Okay. I like it. Shabba. Yes?
Do both statements have to be true and like it has to be more than 30 and
No. So the one we just did,
yeah.
the population is not normal,
So
but
usually-
sample size saves our ass. The first one, sample size not big enough, but it didn't have to be because it's already normal, right? So which one can I not do? Which one of these can we not do? C. Sample, is it normal? Damn it. Sample size does not say this, right? So C, if you saw a problem like that in the book, you cannot do that. You can just say, nope, or you can say, can't do. This is a stats 2 problem, which unfortunately we don't teach. Damn it. So I cannot show you how to do that. Big gross smile. I'm sorry. Does everybody see that? So it's got to be normal to do something. And then which standard deviation I know is going to tell me which thing to do. And how are you going to remember that? You're going to have these crazy ass formulas on your freaking chart that tells you Z goes with sigma and T goes with S. Can't beat that. Okay. The last one. I'm sorry. Go ahead.
Are you gonna throw them short questions like that, like on the test, like?
No, I will never give you a problem that if you don't notice you can't do it, you're going to waste time doing it, and somebody else notices it and they finish and you don't, and I'm up here going, let's do that. That would be so evil. The homework, technically they sometimes have something you can't do. I just tell you, just do it. You could say something like, you know, it's not big enough, and it doesn't say it's normal, but this is what it would be if I could do it, right? Because I'll show you. The book tries to say stuff like all the t-score distributions are normally distributed, but then they have a z-score problem that isn't technically normal, but they want you to still do it. Do you see what I'm saying? So I think they were trying to say everything's normal, just do it. I don't know if you guys are with me or not, but I'm never on a test. The only kind of problem I would give you is something like this, where it's not a full problem, it's just yes or no is the answer and you're done. Does that make sense? Instead of somebody's doing the entire work and he didn't have to. That would suck. Okay. Part D. Is that okay? Can I do something? Yeah, I'm doubly good. It was already normal and the sample size is way big. Which standard deviation do I know? I know S, so I have to use a t-score. I love it. So I'm allowed to use something, and I must use a t-score. Degrees of freedom is 60. And then what's alpha? Now I can say that directly. What's alpha? 0.01. Is that right? 1%, 0.01. So I know I'm going to look at that first column, and I'm going to stop at 60. Stop at 60. There you go. 2.660. So we got a 1.660 and we got a 2.6. Okay, I'll stop. Sorry. No idea what that was. Now, oh shit. Now I can bring back, oh, you're all excited about this. Now that you know about t-scores, I can now make you calculate your own shit. Right? In section 8.1, you had to know sigma. You had to know the population standard deviation, so I'd have to give that to you. Here, if you only know S, you're golden. You can still do something. So let's see who remembers. Take a minute and figure out, if you haven't already, figure out the sample mean and the sample standard deviation for that data. If you forgot how to do it, call me over, ask somebody else, or just sit there and wait. So where do I go from here? I've got my data in there. Where do I go? Anybody help me? I forgot. Where do I go from here? Stat? Calc. One of our stats. Make sure it says list 1. Shaboom. Calculate. Is that what you guys got? So I got my mean. 78.2, we'll say 9, that's fine. What's my standard deviation? What is it? You wish. So, real quick. Sorry. This calculator is dumb. Sorry, little calculator. You. There's no freaking idea. We put numbers in it. It's like, it doesn't have a clue. It's like, here, human, you pick. So what was it we just put in? Was it a sample or a population? It was a sample. So which one must we use? Yeah, the S one, right? So don't be really careful. Don't go, oh shit, I know sigma, I can use Z. Yeah, no, too bad. No, it was a sample we put in there. We have to use S. It just gives us both because the poor little dude is dumb. All right. Was it 15.724? All right. So real quick, is the sample size big enough to do something from itself? Is the sample size big enough? Is the sample size big enough to tell me it's normal? But why is it okay still? Because I tell you it's normal. Yeah. So sample size is only 7, but I do say I took it from a normal distribution, so it's already normal to start with, right? Okay. So now you guys look up the t-score, try to plug it in, and try to get your confidence interval figured out. I'll just stand here. Be very helpful. Well, call me over if you need some help. I can help you. Maybe. I don't know. I would give this half. So real quick, guys, what's the degrees of freedom? Let me just make sure everybody's on the right track. 6. What's alpha? 0.02. So what'd you guys get for t-score? Three, 1, 4, 3. Okay, so everybody's on the right track. Keep going. Yeah, maybe. That might be good. Yeah, okay. One quick place that I see a mistake all the time is people will put a 6 there instead of a 7 because your brain's thinking degree of freedom. That's got to be the full N, dude, right? We're in the N, dude. You guys get that error there? Okay. So we're all either right or we're all either wrong. Okay. Now, one reason I do this problem is to kind of make a point about something. These are grades, correct? This whole thing's about grades. And we're trying to find a 98% confidence interval for the true mean grade. Look at the confidence interval you end up with. What's it say it thinks the grade could be from to? From an F to an A. It's like, oh, thank you. Why does that interval suck so bad? You all agree, it's not the interval's fault. We just didn't put into it what it needed. Can somebody tell me 2 reasons why this might be kind of a wide interval, right? Again, this is from F to A, correct? Not very definitive, not very informative. Why is this poor little dude so wide? Say again? Okay, sure, but more important than that. So we had to use a t-score, that's one thing, which made this number bigger than it was. So that's one reason why. And the other big thing is the sample size is so damn small, right? I only got 7 in my sample. I'm gonna be uncertain about every damn thing. So of course the confidence interval is stupid big. The confidence interval like, shit, dude. Okay, I'm gonna have to be wide to cover your ass for all the stuff you don't know. Does it make, you guys sort of with me? So if I upped the sample size to 70, that would bring the error down by quite a bit, right? So if I assume everything stays the same, but I take a sample size of 70 instead, the error would go down to about 6 instead of 18. Are you with me? Okay, so look, it's a little side. Okay. I don't know if anybody knows, I was up here trying to, look on the other side real quick. Look at that. I mean, that's just beautiful. Give me a break. Look at that wall of data. I kind of have a feeling I don't necessarily want to do this at you today. So what I want to do instead, what I think is probably a good idea, is I want to do one more example of the P hat, Q hat problem, because we really didn't do much of that. And then we'll call it a day, right? And, you know, I try not to take it personal when somebody's so excited about this class ending early, but I understand. I'm happy to because I'm hungry. So let's do one more example of the P hat, Q hat confidence interval. And also, let me just put up here. Those are my things. Now, real quick. Have we seen any other formulas yet that have a plus or minus in them in this class? No. If I have a problem that says create the confidence interval for blah, 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 you're going to use one of these 3 formulas because that's plus or minus. It's going to make an interval, correct? If I don't ask you for a confidence interval, don't use one of these formulas. Are you guys with me? I always get people use these things in the weirdest places. It didn't ask for an interval. Why would you use that? Does that make sense? So here we go. Let's say, I talked to, talked to 812 people, just randomly, just because I was really bored. And 215 say they enjoy statistics. Right. Create the yeah, sure. a 90% confidence interval for the true percentage of people who enjoy stats. Good Lord, Jeff. Now, one little thing in the background here that I do normally kind of ask for, but I might not. How do you show that you're allowed to create the confidence interval? How do you show that for this problem? You have to show me that. Before you create it, you got to show me you're allowed to. How do you show me you're allowed to? You say, well, I enrolled in your damn class, Jeff, so therefore I got to do this shit. No. What about this problem do you have to check to make sure this is something you can actually use z-scores on?
Sample size greater than 30.
No. Careful. What is this a test for? A mean or a percentage? It's a mean. Sorry, it's a percentage. I was going ahead in my brain. For means, n greater than 30 is the test. For percentages, what's the test? NP hat at least 5, NQ hat at least 5. Right? I guess kind of. And one really cool thing, how many formulas are here? 3. How many of them involve the mean? 2. Why 2? Because they have to use Z or T, depending. How many involve a percentage? 1. For percentage problems, it's either normal enough and I use a Z-score, or it's not normal enough and I don't do shit. You guys hear me? You never use T-scores with percentage problems. They weren't invented for percentage problems. So either it's normal enough and you use a Z-score, like the formula says, or it's not normal enough and you do nothing. Okay, go for it. We'll do that next time. Ooh, third option. Ooh, okay. Somebody got P hat figured out? How did you figure it out? What do you do? No? Are you guys all just doodling? Huh? 215 out of 812. So 0.26 something?
2648.
2648. 2648. So you can make that 265 if you want to. 2648 is perfectly fine. It's got to be at least 3 decimal places for percentages. All right, so then what's Q hat? 7, 3, 5, 11. Okay, so there we go. Sweet. Now, you could do the work 0.265 times 812, but I already know that's going to be 215. Now, if you do the work, it's not going to be exactly 215 because we rounded 0.265, correct? So who got NP hat? 0.265 times 812, you got close to 215, correct? Did anybody do that yet? What'd you get?
215.18.
Beautiful, which I'm going to call 215 because I ran greater equal to 5. And then the rest, which would be about 597.
96.82.
Kick ass. And you rounded to that? Beautiful. So it just got to be at least 5. What does that mean? What does all that mean? What does this mean?
100 cats a go.
Hmm? Yeah, it's normal enough. Good. It's normal enough for me to do this. I like it. So if either one of those were either one was less than 5, you officially cannot do this. And now it's just plug and chug, right? I want to be how confident? 90%. So what's alpha? What's alpha? 0.10. I like it. So now you know which column to look at. I'm still going to use the t-score chart. Is everybody decent with that? I always get somebody that's like, what? It's a z-score. So I just go all the way down. And then I get a z-score. I like it. If I stop, I get a t-score. If I go all the way down, I get a z-score. So what z-score did you guys get? 1.645. Kick ass. 1.265. Choose the 5. Choose the 5, Jeff? Sure. 265. Give or take. Blah blah blah. What do you think, Jeff? 216. So square 4. You're gonna try this in your head. Oh, why, Jeff? Somebody help me. 270 is like, I don't want to do it in my head. What is it? 0.24? Hmm? Oh, I see what you mean. I just want to know what the error is. Sorry. No? Okay. Anybody got the error? Error? 0.0? 254? Okay. So, and again, I'm crowdsourcing. I could be wrong. I don't know. Not that I don't have faith in you. And now you just subtract and add that, right? So you're going to get 0.2396. Who is it? 2395? Okay. Up to 0.2904? Okay. Alright, so then we would say we are 90% confident that the interval, 23.95% to 29.04% contains the true percentage of people who enjoy statistics. I'm not sure if anybody here is like, that seems high, Jeff. Oh well. So again, the nuts and bolts of these things, as so often happens, is much more accessible than the freaking concept that went into building them. That happens all the time. So that's hopefully not that bad, these confidence intervals. Okay, so next time we'll do this. That's enough for today, I think. Don't forget your stuff, please, dear God.